Alright, so with this, we're going to talk about double angles. Now, what is a double angle? Suppose we had some angle. Ooh, that was a really bad drawing, so we'll try that again. Page. Suppose we had some angle like x. And we wanted to know not necessarily about angle x, but suppose we wanted to know about angle 2x. Well, a double angle is talking about if we know the sine and cosine of our single angle x, then can we use that somehow to find the sine and cosine and tangent and all of the other ratios for our double angle? Now, some interesting thing about double angles will sometimes move. So for instance, if I wasn't talking about this angle that looks like it's close to pi by 4, if I was talking about this angle that looks like it's close to pi by 2, if I double this angle, it'll actually change it from quadrant 1 to quadrant 2. So sometimes double angles will change a sign. Now let's consider a double angle formula using our compound angle formula. So just let me rearrange here. And I usually start with sine, but hey, let's start with cosine. So suppose we wanted to know the cosine of some angle. Let's go 2x. Well, if I wanted to know the cosine of 2x, geez, I don't have anything that helps me with this. What if I wrote it like cosine of x plus x? Then I could go back and use my compound angle formula for cosine. Now, the compound angle formula for cosine is that weird one. It's cosine of the first angle times cosine of the second angle. But instead of if it's positive here, it's going to end up being negative here. So then minus sine of the first angle times sine of the second angle. And you can see with a lot of our composite formulas, when we have that first angle, second angle stuff, when we're dealing with double angles, it's just going to be the same. So we'll be able to take this cosine and cosine and multiply them together to make cosine squared x minus sine squared x. And so in fact, this is a double angle formula for cosine. That's one of the ones that's really quite useful to know. Now, you could go through and find a double angle formula for sine using the exact same strategy. Just take sine of 2x, break sine up into x plus x, and then apply the compound angle formula. Now, if you did that with sine of 2x, this is what you would get. So they're slightly different. One of them looks an awful lot like the Pythagorean identity, which is kind of nice and it will be useful eventually. And the other one is neat because it deals with just a product, so it becomes useful for that. So this was the proof of the cosine double angle formula. But wait, there's more. We're going to quickly change this into two additional useful forms. And we're going to make these changes using the Pythagorean identity. Now, remember, your Pythagorean identity is that cosine squared is equal to 1 minus sine squared. So that tells me that cosine of 2x is actually equal to 1 minus sine squared x minus sine squared x, simplifying to 1 minus 2 sine squared x. Now that's just one additional version of it. This is perfectly equivalent to this and this. So this is another version of the cosine double angle. And we can do the same thing, but instead of changing this cosine squared, we can change sine squared. So we'll have cosine of 2x is equal to cosine squared x minus, and then I'm going to do this part in brackets because sine is 1 minus cosine squared x. Ooh, ran out of page there. There's a bracket closing that off. As I distribute the negative in front of that bracket, I'll have cosine squared x minus 1 plus cosine squared x, which means my second, or rather I suppose at this time my third version, is 2 cosine squared x minus 1. And so those are your double angle formulas for sine and cosine. Oh, I'll move my book so you can see it. And you could go ahead and do an extension to figure out what the tangent one is too. So you'll notice that some of these will not appear in your formula booklet. They absolutely would be tested material in grade 12U functions. IB just takes a little bit of a different look at identities from grade 12U functions, but I still prefer knowing these things because of the great connections to theory of knowledge. Take care.